All right, 2:40. Let's get started. So, announcements. Friday was the exam, Friday and Saturday. And so you all got to see what one of the exams, what they're like. And hopefully it was an acceptable experience for you. Let's see here. The score to grade conversion spreadsheet is now posted in the WebAssign announcement area. So if you go to WebAssign, here in the announcement area, come on down, your grade through exam 1, you can download the spreadsheet. And I have it up here. And here you have all the different grades that you will get throughout this semester. And the green ones are the ones you've completed already. And so you can enter in the scores. Don't enter the percents, enter the scores that you've gotten for these. So in the homeworks, we've had 3 homeworks, and maybe you aced all 3. Most people ace the homework since you get 3 attempts on every question. And then for the exam, I don't know, let's say you got 20 out of 25, then you'd have a B. Your class rank would be 128 out of 311 so far, or 311 combined between the 2 sections. And I don't know, if I got a 23, then I have an A. I'm in top 27 students. I got a 18, C+. Anyway, you can play those games. Now, I should point out, I dropped 1 homework automatically, and that's already going into this. So whichever homework you had the lowest score on is dropped automatically. I can remove one of these, and you see the score doesn't change at all. Though if you miss 2 homeworks, then that can have a really bad effect, and that's because your homework grade is, we've had 3 homeworks, I dropped 1 automatically, so I'm averaging the other 2. If you have a 0 for 1, then that's not good, but as you do other homeworks, that will have less of an impact. And also I offer an extra credit opportunity in lesson 5 to drop a second homework. So if you've missed 2, you can get rid of the second one as well. But most of you have done all 3. Maybe you got some 9s and 10s. Anyway, the grade you have will be mostly dependent upon the exam, since most people get the same scores for the homeworks. Questions about that? Everyone's downloading it and trying it now, I'm sure. And, before this, I like teaching the first third before we have our exam, because everything is, happiness and butterflies, but then you take that first exam, and as I've already explained, being a large lecture section, the university has a requirement that the average GPA is 2.6 to 2.7, and that means half of you have a B- or higher, and half of you have a lower grade at the moment. And I know that can be a shock, particularly for first-year students. You're all Carolina students. That means you did very well in high school, near the tops of your classes, and then you come here, and I think I said this before, and it sounds like a terrible thing to say, but I say it jokingly, now half of you are, by definition, below average, just because you're playing in a higher league. And don't take that personally, it's just to set expectations. If you're a straight A student in high school, this may be a little bit of a shock, but it's just an astronomy class, so don't get too frustrated about it. And again, half of you are in the top half of the distribution, are doing well and probably happy with your results. Anyway, I'm happy to take any questions on that. Okay. Well, moving on, homework 4, I've moved from this Friday to the following Monday. You can already see that in WebAssign. It's going to be due Monday, October 5th. I'm still a little bit behind, so I'll need that extra day to get through the telescope section, but that should be sufficient to get us through, and then we'll begin lesson 5 on that Monday. And that's it for announcements. So if there are no questions, we'll go into the warm-ups. Okay. For the warm-up, just one warm-up question. Should say I did an almost all-nighter, so if my lecture is a little bit scatterbrained. I apologize for that. I'll do my best. So our warm-up question, before we were talking about telescope design, detector design, disperser design. So this is asking about dispersers. The question is, uses interference to disperse different colors of light. Is it A, a photographic plate, B, a CCD, 3, a prism, or 4, a grating? Okay. Let's come back here. 21 responses. I'll give you another 5 or 10 seconds. Okay, let's take a look. The other class got it wrong, as did you. So it's not prism, but I can understand why you chose prism. What you did figure out, I would send you into breakout rooms, but I think you've already figured out it's not 1 and 2. And if I say it's not 3, that means it's 4. So I'm not going to send you into the breakout rooms. It's not 1 and 2 because 1 and 2 are detectors. Photographic plates, CCDs, now CMOSs, they are detectors. And we're asking specifically about dispersers. So prisms disperse light and gratings also disperse light. But prisms don't use interference to disperse the light. What do they use? What's the physical process that disperses light in a prism? Not interference, but one of our 2 types of telescopes is named after this.
Refraction.
Refraction, yep. Uses refraction. And so it's grating. Grating uses interference. And I know I went through the different types of dispersers and spectrographs pretty quickly the last lecture on Wednesday. So hence the warm-up question, so we can just readdress the topic. But, here's a prism, and it uses refraction. And here is a grating. And what the grating is, it just looks like a piece of plastic there. Actually, if I hold it up to the light, you may see some, well, no, I'd have to have a source. You saw some colors coming through. What it is, it's like Young's double slit experiment. Except instead of 2 slits, it's many slits, but it works pretty much the same way. You end up with the interference pattern. Light is traveling as a wave, and it's constructively and destructively interfering with itself, giving you different orders. The 0th order is the light that goes straight through, and then you have a band on either side, and then another, and another, and another. Can't see it very well here because that's just a black and white printout, but you pull up that same slide here. And so here we see the different orders, but once you're in 1st order and 2nd order and so forth, it spreads the light out. And you may remember when I had the element lamps here a few weeks ago, and you were identifying what element it was, I was holding the grating up to the light here, and, sorry, dot cam, on the grating up to the light, and you could still see the lamp straight through, that 0th order. But off on the side, either side actually, you could see a spectrum. Sometimes I was holding it such that you could only see 1, but if I moved it around a little bit, you probably noticed there was a spectrum on either side. So you can zoom in here. And astronomers mostly use gratings in their spectrographs. Prisms are bigger and bulkier, again, dot cam, bigger, bulkier, not as efficient. They scatter the light all over the place. Sometimes they're useful, but if I want a really high resolution spectrum, I'll use a grating. Okay, questions about that? Okay, so last time we were talking about design, the last couple of times, different types of telescope design, detector design, disperser, spectrograph design. Let's switch gears a little bit and talk about telescope size. Let's get rid of this. Maybe make this big, but put that back up. Okay, telescope size. So historically, we've been building bigger and bigger and bigger telescopes, the professionals have anyway. And there's a reason for this. Telescope size comes with advantages, and there are two specific reasons why we build bigger telescopes. The first is called light gathering power. And this one's pretty straightforward. The bigger the telescope, the bigger the mirror, the bigger the collecting area. It means you can collect more light in the same amount of time. So a clear advantage. The second, and we'll come back and explore that. Let me just briefly mention the second. It's called resolving power. And this is how much the telescope blurs out whatever you're looking at. And larger telescopes will blur your image less, smaller telescopes more. And this is separate from the blurring that's caused by the atmosphere. We'll address that in this class as well. But let's start with light gathering power. Light gathering power is really just about the collecting area of your telescope. So let's look at this example. We have, this is the galaxy Andromeda, our sister galaxy. It's about the same size, same mass as our galaxy. We're gravitationally bound to it. In fact, it's heading straight towards us, or we're both heading straight towards each other. About 3 billion years we'll merge and become a common galaxy. But anyway, the picture on the left was taken with a telescope of a certain size in a certain amount of time. Let's say it was a 10-second exposure on a telescope of a certain size. The picture on the right, same duration, 10-second exposure, but on a telescope with twice the collecting area. The area of the mirror is twice as big. And so you get more light in that same amount of time, and so you can see more details, more structure. Here you're just seeing the bright central regions, but here on the right, you can see you can begin to see the edges and the outskirts of the galaxy. If we were to use an even bigger telescope and bring in more light in that same amount of time, we'd see more detail. So clear advantage there. Let me ask you a question. So how much more light would you collect with a 5-meter telescope, 5-meter diameter, like the Hale telescope, than with a 1-meter diameter telescope? Just shout it out. The other class got this wrong too. So 5-meter diameter telescope, 1-meter diameter telescope. The 5-meter diameter telescope will of course collect more light, but how much more light? Venture a guess, anyone?
5.
Was that 5?
25.
25, yes. Most people think 5, and that makes sense, but the answer is actually 25. Pull up the dot cam, explain why. So the area of a circle, anyone remember the equation? Area of a circle is?
Pi r squared?
Pi r squared, pi times the radius squared, yep. And now we normally measure, well, anyway, all telescopes, if you look from the top down, they look like a circle. The mirror is a parabola, but looking at it face on, it looks like a circle. But we measure those mirror sizes in terms of their diameter. So let's convert from radius to diameter. Diameter divided by 2 is the radius. You can square that, and we end up with some constant in front, pi over 4 times.
Can you move the camera over so we can see the work you're doing?
Are you blocked on the right by our faces? Is that it?
Oh yeah, should I move? Yeah, never mind. Thank you.
Yeah, it's good advice because the recording will put faces there anyway. You wouldn't be able to see what I'm writing, so thanks. So the constant really doesn't matter. The key thing is area is proportional to diameter squared. You can look at this as a ratio problem. In this case, we're comparing a 5-meter to a 1-meter. And since it's proportional to the square, for example, if you doubled the diameter, 4 times the area. Triple the diameter, 9 times the area. 5 times the diameter, 25 times the area. Okay, so the Hale telescope collects 25 times as much light in the same amount of time as a standard 1-meter diameter telescope would. And this provides 2 advantages. One is you can push the cutting edge. You can observe fainter things. We call this deeper. It's a deeper astronomical image, so you can see fainter things, maybe things that have never been seen before. Now, when the Hale telescope was first made, mid 20th century, there were no other 5-meter diameter telescopes, so you can see farther out into space and fainter objects and push the cutting edge. But the other way you can use a large telescope is you can do the same science that you were doing on that 1-meter telescope, but you can do it 25 times quicker on a 5-meter telescope. That means you can do 25 times as much of it. And some science is about pushing deeper, fainter, seeing that thing that's never been seen before. But some of it is studying large numbers of objects, and bright objects are still interesting, but sometimes what we need to learn, we can't learn from an individual object, but from studying a whole population of them. So in that case, you want to image as many as possible, and a large telescope is useful in that sense. You could do more of the 1-meter diameter work in the same amount of time. Okay, so those are the two advantages of light gathering power. Let's consider some large telescopes, just show you some of the big telescopes in the world out there right now. This is Mauna Kea in Hawaii on the Big Island. It's 14,000 feet up, which is an interesting elevation to work at. Most people, actually most astronomers, don't work at the top of the mountain. There's a way station halfway down. They work there because there's more oxygen to breathe. Once you get up to 14,000 feet, there's 30 to 40% less oxygen. And you notice it. I've used these two telescopes here, the Keck telescopes, before as part of a group, and we used them remotely, so I wasn't there. My first trip to these telescopes was actually 2 summers ago. And I went up just almost as a tourist just to see them. I wasn't actually using them, and went up to the top and really noticed the lack of oxygen. You get lightheaded pretty quick. So even the astronomers, they normally work from halfway down the mountain or completely remotely over the internet. But some people do have to work at the top of the mountain, changing instruments, repairing things, and they send them up with oxygen monitors, and they put them up there in teams. Some people adapt to it pretty easily. Other people have a very bad time. They get headaches and have to go back down and spend some time acclimating. Sometimes people pass out, and that's why you put them up there in teams. But you can go up there as a tourist. You're just not supposed to stay very long, and the idea is you're in a group of people, so you're not in danger. And actually, to the human eye, the stars look better from halfway down than at the top of the mountain. That seems backwards because you're higher up, you're above more atmosphere. There's less atmosphere messing up your viewing. But if you deprive yourself of 30 to 40% oxygen intake, your eyes don't function as well. Your brain doesn't function as well. And so the sky actually looks blurrier to the human eye. And you're better off just staying farther down the mountain to look. But no one's, with these telescopes, no one's looking with their human eye. There are no eyepieces on these telescopes. They're CCDs and CMOSs and scientific instruments. And for them, it's best to be above as much atmosphere as possible. Anyway, you have some large telescopes, some of the largest telescopes in the world up here. And there are other sites as well. I'm just starting with this one. This is one of the best ones in the world. You have the 2 Keck telescopes. They're 10-meter diameter mirrors. This is California System Schools and Caltech kind of leading the effort. They built the Hale telescope mid-20th century. By 1980, they upgraded from 5 to 10 meters with the Keck 1, and by the early 90s, Keck 2. They're kind of ahead of the game. I don't know if I'd mentioned this before, but there are kind of 3 major entities out there in the world, astronomical entities. You have European astronomy, you have American astronomy, and you have Californian astronomy. They've been so far ahead of the curve for so long, and their resources are comparable to the rest of the United States put together. You kind of have to look at them separately. So they developed these 2. This over here is Subaru. This is a Japanese telescope, an 8-meter diameter telescope. And over here we have an example of American astronomy's current largest telescope, Gemini North. The constellation Gemini is twins. There's one here in the north, and there's another down near the Prompt telescopes in Chile, Gemini South. So 8 meters. And there are a handful, I'll show you a few more in just a second. but there may be probably less than 10, 8 to 10 meter diameter class telescopes in the world. And they're currently the largest. And we've been here for a while. You know, the first one was built in the 80s. They've been building the rest of them since. And the time has come to start building larger telescopes. There's a plot, I don't have it up on my computer, but the largest telescope in the world is a function of time. There's a very clear progression. And for this moment in time, we should be building 30-meter telescopes, 30-meter diameter mirrors, and that's what's going on. 3 of them are being built, as you could guess, from the Europeans, the Americans, and the Californians. The Californian one's called the 30-meter telescope, TMT. It will be given a name if it hasn't been given one yet. I can't recall, actually. And it's being built right now up on Mauna Kea. And just to put it in perspective, here's the Hale 200-inch mirror, 5-meter diameter. Here's the Keck, and this will be the TMT. Once you get to this size, you can't build a single piece of glass. They're hexagonal, segmented mirrors where the glass is put together. And it's actually a little bit challenging for the Californian effort. They're building on Mauna Kea, and Mauna Kea is also a sacred native Hawaiian site. And they've never been happy with the telescopes up there. And there were court battles. The astronomers weren't always very sensitive about this either. So there were court battles, and back in the 70s, they concluded that there'll be no more telescopes. If we want to build a new telescope, we have to tear one down. So what astronomers are doing is they tear down one of the small ones and then build a large one, which just results in more court battles and protests blocking the road and stuff like that. It's challenging. I'm not taking one side or the other, but construction is proceeding, but very slowly because of this challenge. The Americans and the Europeans, they're building their large telescopes in the Chilean Andes. And the Chileans just love us coming down and building telescopes there and spending our money. And you know, they're not sacred mountaintops or anything. So it's a much different environment, easier to build the telescopes there. And speaking of which, here's an example of the European largest telescope in the world right now. I did say that all 3 entities are building 30-meter telescopes. The Americans' 30-meter telescope's a little bit smaller. It's 20-some meters. And the Europeans will be a little bit larger. I think it's 40-some meters. And there's no guarantee that all 3 will make it through. These are very expensive. Each one is like $100 million. But anyway, here are the current large ones for the Europeans. These are called the VLTs, which stands for Very Large Telescopes. We aren't always creative with our acronyms. And these are in the Atacama Desert, in northern part of Chile, very high up. 4 8-meter diameter telescopes, and they can also work together as a single unit, which is effectively a 16-meter diameter telescope, which is the largest in the world, at least for the time being. The 30 meters will beat them. So, questions about light gathering power in large telescopes. Okay, let's move on to resolving power. This concept's a little bit more subtle. Resolving power here. And just get my notes to the right place. Yeah. I'll probably go to a new page. So resolving power is how much a telescope blurs out the image. Not the atmosphere. The atmosphere also blurs out images, and we'll talk about that separately, but how much the telescope does. No telescope is perfect. And it's impossible to make a perfect telescope. And I'll tell you why in a second, but this diagram kind of illustrates the effect with size. At the bottom, we're looking at 2 stars with a large enough telescope, large enough that can resolve them, that can separate them. Though if you go to a smaller telescope, they blur out, and now they're kind of touching each other. They're not fully resolved, they're partially resolved. Now up here's an even smaller telescope, the blurring's more, and we don't even know what we're looking at. Is this 2 objects? Is this a single object, like a galaxy on its edge or a comet? You don't know. So there's an effect, and to explain it, we go back to diffraction, which we've already spent a lot of time talking about. So here's a barrier, just to remind you, with an opening, and if the opening is about the same as the wavelength, here we have these plane parallel waves, so light coming from far away, so it's nice and flat when it hits the barrier. And then if the opening's about the same as the distance between the crests or troughs of the wave, you get this maximum bending, that's diffraction. Now, what happens if I take away one side? Instead of a slit that the light's going through, let's say it's going past the edge. And actually, we'll turn this into a mirror in just a second. So here's light coming down, striking the edge of a mirror. The light over here passes right by. It's not disturbed at all. But the light that comes down and passes right on the edge will bend. It will diffract as it's going around. Just like you see here, it maintains that same pattern. Waves just have a hard time going around sharp edges, even if there's only one instead of two. Now, instead of a barrier, let's imagine this as a mirror. Let's put a reflective coating on the top here. So as the light comes down, some will pass by it, diffracting as it goes near the mirror, and some will bounce off it. Here you see the light coming back up, but it will also diffract off the edge, the reflected light. Again, just waves have a hard time with these edges. And so if this is a mirror, well, this is a flat mirror. It's not going to focus anywhere, but you can imagine a curved mirror, a parabolic mirror. Light comes in, it's bouncing off, and most of the places on the mirror it bounces off just fine, like you would expect. But near the edges, it gets bent, deflected, diffracted as it bounces, and that stuff will not go to the focal point as you want, and it causes the image to become a little bit blurred. So any telescope with an edge, which is every telescope, will blur the light to some degree. Here we see, this is actually the mirror to UNC's 4-meter diameter telescope in the Chilean Andes near the Prompt telescopes. And just like any telescope, it has an edge. And as the light's coming down, if it's bouncing too close within some distance of the edge, it will not go to the proper focal point. Now you can see why big telescopes are better from this figure, which I made myself in Microsoft Paint using my mad paint skills. And we have a large telescope and a small telescope. Gray is the area where the light bounces as it should. But within a few wavelengths of the edge of the mirror, that's where you're going to have the diffraction. This is the bad reflection area. So you have good reflection area, bad reflection area. And you can see from the big one here, you have a lot more good area than bad area. If you go to the small one, you still have to go that same number of wavelengths in. And so you're going to have a higher fraction of bad reflecting area compared to the good. So you can see it. As you go to smaller telescopes, the focus will be worse because you have a higher and higher fraction that is in this bad region. Let's look at some examples, and then I'll put down an equation. And this is one of those cases where Zoom lectures may not be the best for this. And what this figure is showing you is different levels of blurriness depending on your internet connection and my internet connection and data throughput rates. This is supposed to be the crispest, cleanest of these, though you may not see that. That may not come across in the recording either. But anyway, on my monitor, this one's really crisp. This is, again, the Andromeda Galaxy, and I can see all sorts of stars in detail. The blurring in this image is about 1 arcsecond, which is typical of what you get from the atmosphere. Now, we're not talking about atmospheric blurring, that's coming, but imagine a telescope that's small enough that its natural blurring scale is similar to what the atmosphere does, 1 arcsecond. And this is the quality image you get. Over here, we're looking at 5 arcseconds of blurring. And so this would be, a smaller telescope, about 1/5 the size, and then Andromeda would look like this. And again, I don't know if you can see it over the internet feed, but this is much blurrier. If you go up here, this is 1 arc minute of blurring, so 60 arcseconds. That's comparable to what the human eye does. The human eye, as we talked about, is a telescope, a very small telescope. And if you look at Andromeda with the unaided eye, you won't see it. You don't have enough light gathering power to bring in enough photons to see it. But if you could, it would be this blurry. because small telescope. If you have an even smaller telescope, smaller than the human eye, this is an example of 10 arc minutes. So this would be a telescope like 1/10 the size of the human eye. We don't make them this small, there's no reason to, but that's the kind of blurring you would get. So you can see the effect here. Okay, let me put up the equation for this. Okay, again, this is under resolving power. And so theta is the symbol that we use for angles. This is how much the light is blurred out. So we sometimes call this the blurring scale of the telescope, or the angular resolution of the telescope. It's sometimes called the diffraction limit, because telescopes are limited by diffraction on the edges, and also resolving power. So it has all sorts of different names. But it's how much the light is blurred out. And it's given by 0.25 arc seconds. The 2 hashes there means arc seconds, times the wavelength measured in microns, micrometers. That's the Greek letter mu from micron, divided by the diameter of the telescope measured in meters. And just to remind you, 1 micron, 1 micrometer, is 1,000 nanometers. And the human eye works from 400 to 700 nanometers, so that's 0.4 to 0.7 microns. The boundary between the visible and the infrared is roughly a micron. Okay, so you can see the bigger the diameter, bigger number in the denominator, less blurring. And we can calculate. As I change the telescope size, I get less blurring. But there's this other factor, the wavelength. The wavelength also matters, which makes sense because that bad reflecting area, it's within a few wavelengths of the edge of the telescope. So if I want to reduce my blurring, I can use a bigger telescope, but I may not have a bigger telescope, but I could go to a shorter wavelength. So here are a telescope, same size telescope, and here I'm using a longer wavelength, so more of the edge is reflecting poorly. Here I'm using a shorter wavelength, so less of the edge is reflecting poorly. So you can see with the shorter wavelength, I have a lot more good area compared to bad, and I'll have less blurring. Put up the dot cam again. And so up here, the shorter the wavelength, the less blurring as well. 2 ways you can do it, bigger telescope or shorter wavelength. But sometimes you don't have a bigger telescope, and sometimes you can't go to a shorter wavelength. Maybe the science you're doing has to be done at a particular wavelength. Anyway, let's work out an example here. Shift that over so the right-hand side is not blocked. Let's take the Hale telescope, which has a diameter of 5 meters. And let's say you're looking at a wavelength of 500 nanometers, kind of in the middle, close to the middle of the visible spectrum. So you want to convert that to microns. Again, there are 1,000 nanometers in 1 micron. Nanometers cancel. And so that's going to be 0.5 microns or micrometers. So the angular resolution of the Hale telescope at this wavelength would be 0.25 arc seconds times 0.5 over 5. 0.5 and the microns cancel, 5 and the meters cancel. So that's 0.5 over 5 is 1/10. So this will be 0.025 arc seconds, which is a really small angle. So the Hale telescope has the ability to image things that crisply, but it never does because there's another limiting factor. And what's that limiting factor? Hinted at it, mentioned it a number of times.
Atmospheric blurring?
The atmosphere. Yeah, the atmosphere will blur things out a lot more than this. So the Hale telescope, at least when it was first built, mid-20th century, the plan was to never take advantage of that angular resolution, The plan was to build a big telescope to collect a lot of light gathering power. But as we'll see in not this lecture, but the lecture to come, we have since learned how to correct the atmosphere and undo its blurring properties. And we can take advantage of at least some of this angular resolution on our large telescopes now. We can get a lot closer to the diffraction limit. But a few things to come first. First, we have to talk about the atmosphere. Okay. So atmospheric blurring. Write that here. The bane of astronomers' existence is atmospheric blurring. Well, no, funding is the bane of our existence, but this would be a close second. Atmospheric blurring. It's also called seeing. If you go to observatory, you can ask, what is the seeing tonight? How much is the atmosphere blurring the light? It varies from night to night, and it varies from place to place. Typical is about 1 arc second. For most, astronaut, not typical anywhere on Earth, but typical for a professional telescope, professional observatory, 1 arc second. Now, sometimes you can be at a great site, one of the best sites on the planet, and have a great night in terms of the atmosphere behaving very well for you. And you can have something like 0.2 arc seconds to 0.3. You can get that good, like a quarter arc second. It's very rare, but you can get that. And then you have places like Chapel Hill. We have Campus Telescope, Moorhead Observatory, and it will be 2 arc seconds to 10. 2 to 3 is typical for most places that, on the surface of the Earth that are not intended for observatories. And sometimes it can get really bad. I've seen 10 arc second seeing from the Chapel Hill telescope. But why? What causes this? So it's caused by the properties of the atmosphere. In this figure, you see the light coming in from space, nice straight rays, but as it enters the atmosphere, it starts to wobble around. And that's because the atmosphere is something. It's not nothing. When it is in space, it's traveling through nothing. But the atmosphere is something, just like a prism is something, glass. When light goes through glass, it refracts. When light goes through air, it also refracts. Not as much, just a little bit, but it does. So let me draw what the atmosphere is kind of like. Slide this over. Down here on the ground, we have our observer there. I attached his arms to his waist. Now he has 4 sets of arms. Good enough. That's our observer. And then we have the atmosphere. The atmosphere is not a large monolithic structure. It breaks into cells and pockets. And I won't draw them all, but they go all the way down to the ground. And some of these are a little bit warmer, some are a little bit cooler, maybe just a fraction of a degree. Maybe this one's hotter, this one's colder. And if gas is hot, what does it do? Expand or contract? Expand. So this pocket may expand a little bit, which means its density will drop, and so it refracts the light less. This one's a little bit cooler, it contracts a little bit, the density goes up, it refracts the light more. And so let's just draw a light beam. I'll exaggerate, what's going on there, but it's zigging and zagging as it goes through. By the time it gets down to the observer, he doesn't know what the atmosphere is doing, at least not without some special technology that we'll talk about later. So he sees the star coming from over there when in reality, it came from over there. Now, I exaggerate greatly. The angular shift is, arc seconds, not degrees as I've drawn here. But that's only half the story. If the atmosphere just would stay put, even if it's messed up and jumbled like this, if it would just stay put, all the stars would be in different positions, but they'd be nice and crisp. But that's not what happens. The atmosphere is constantly moving. These cells are getting bigger and smaller, changing their temperature, merging, breaking apart. And so even 100th of a second later, as it goes through, it will appear to be coming from a different direction. It bounces around. So imagine a really bright star, bright enough that you could image it in 100th of a second. I should write that down. That's kind of the time scale over which the atmosphere is changing, 100th of a second. It's like video rates, similar to video rates. So if you have a star that's bright enough that you could detect it on video, you would see it bouncing around, and that's what you see here. The little black dot is the telescope's diffraction limit, and you see it moving around. The atmosphere is pushing it all over the place. It's not only changing its position, it's magnifying and demagnifying it. And this is actually why the stars twinkle, because the atmosphere is changing, it's magnifying and demagnifying. And it's why planets don't twinkle. So you may not have known that. Stars twinkle and planets don't. If you're looking up at the sky at night and you see a bright point of light and you're wondering, is that a star or a planet? Look and see if it's twinkling. If it's not, it's a planet. And the reason that planets don't twinkle is because they're actually pretty big. You can't see it with the human eye, but if you're in the lab, you've been taking pictures and you realize, yeah, they're extended. So here's a planet's disk and here's a distant star. Star is much bigger, but so far away, it's just like a tiny point. And that star can live in a single atmospheric cell. Here I'm drawing some atmospheric cells as we look up at the star. So this cell may magnify it, but a fraction of a second later, another cell may move in place of it and demagnify it. But the planetary disk is so big that it takes many cells to cover it. And some of these will be magnifying and some will be demagnifying, and so it kind of averages out, and that's why the planets don't twinkle. Little nifty fact. Okay, so that was an aside, but if it's bright enough, you can see it moving around, you can see it magnifying, demagnifying. But most things we look at are not bright, right? We've studied the bright stuff to death. We're interested in the faint stuff. And if it's faint, it's going to take more than 100th of a second to get enough light to actually see it. So suppose you're imaging some faint galaxy and you have to image for minutes or even hours to see it. And maybe it's a spiral galaxy, and a perfect world would look like that. But the next 100th of a second, the atmosphere shifted the light, and then 100th of a second after that, and after that, and you can see it gets blurry as it bounces through this region. That region over which it bounces, that's what we call the seeing. That's the atmospheric blurring. It's typically 1 arc second. And anything we have to image for an extended period of time will be blurred out by the seeing. Well, what can we do about it? So there are a couple things that we can do. I'll mention 2 of them now, and I'll save the coolest one for next time. First, you can go to a longer wavelength. If the atmosphere is like a bunch of lenses or a bunch of prisms, because remember, lenses are just a bunch of prisms put together, we know that lenses and prisms refract different colors of light differently. The red light is deflected the least, the blue or violet light is deflected the most. So the atmosphere is going to scatter the blue extra all over the place, the red a little bit less. So this is that point in your college career when you learn why the sky is blue. And the light's coming down from the sun, the blue light scatters more. And so some of the blue light coming down here will be, let's say you're standing here, you'll see blue light scattered into your eye from over there and from over here and up here and up here, and everywhere. That sunlight, the blue scatters more, so you get more of it scattered into your eye from directions that are not directly looking at the sun. Now, if you look towards the sun, it should be a little bit redder because the blue light has been scattered out, but it's a small effect most of the time. Because most of the time you're not looking through a lot of atmosphere. If you're looking straight up, you're looking through what we describe as one atmosphere. It's not a lot. It's enough to scatter the blue, but it doesn't scatter the red nearly as much. But if the sun is on the horizon, like a sunrise or a sunset, you're looking through a lot more atmosphere. Draw that. Here's the Earth. Here's Earth's atmosphere. I'm probably drawing it too thick. It's really, really thin. If we're standing here and looking in this direction at the sun, then we're just looking through a little bit of atmosphere. Some of the light will come into the atmosphere here, and the blue gets scattered all over. Some here, and the blue gets scattered all over, some into our eye. But you're only looking through a little bit of atmosphere. Here's our horizon. I'll extend it off into the distance. So if the sun is here, near our horizon, that light is going through a lot of atmosphere. And so if you look at the sun on the horizon, all the blue is scattered out. And a lot of the red is scattered out as well, but what's left behind is much more red than blue. And that's why sunsets are red and sunrises are red. And it's not just the sun, it's anything down there. If you've seen the moon rise, it rises blood red. Even bright stars and bright planets, you can detect the color. If it's a faint star, then again, the human eye, the cones don't work, and you rely on your rods, which are not color sensitive. But if it's sufficiently bright, it will look red on the horizon, and less so the higher up it goes. So, why the sky is blue and why sunrises are red. So that's one approach. You can go to a longer wavelength. But sometimes, and think about it, the telescopes, the longer the wavelength you go, they blur more. The atmosphere, the shorter wavelength you go, blurs more. So there's some kind of sweet spot. And the science that you're doing may not land in that sweet spot. You may have to be at a frequency where it's not optimal. You may not have the option of going to a longer wavelength. So what else can you do? Well, if you can't go longer, you can go up. You can get above the atmosphere. And that's why we're building our telescopes on these tall mountains and getting to heights where it's harder to breathe, because we're trying to get above the atmosphere. No atmosphere, you can't breathe, right? So getting this high up, we're above a third of the atmosphere, 30–40% of the atmosphere, so 30 or 40% less blurring. So that's one way you can challenge this, is to go to higher elevation, look through less atmosphere, and you can take this to the limit. What can we do? I mean, we're not going to go on Mount Everest, right? Because not safe, too hard to work. But what can we do to get higher than this? We can go to space, yep. So here's the Hubble Space Telescope, and this would probably be the last thing we discuss today. And everyone thinks of the Hubble, well, first of all, it's amazing. It was launched in 1990, and it's still operating 30 years later. Most space telescope missions, maybe 5 years, and then it doesn't function anymore. You can't keep the equipment running forever and ever. But this was built in low Earth orbit, so we could go up and fix it as it broke, improve it as technology advanced here on Earth. And so it used to be visited by the space shuttles. We don't do this anymore. So as Hubble breaks, it won't be fixed, and it'll be retired in time. But it's still up there, it's still functioning. Amazing telescope, and everyone thinks it's the biggest telescope ever, but it's not even close. I go back to my dock cam here, just to put it in perspective. Let's say this is Keck, which is a 10 meter. Here would be Hale, 5 meter. Here would be Hubble, 2.5 meter. So, and now we're talking about building 30 meter telescopes, which are just huge. So not the largest telescope in the world by any means. Lots and lots of telescopes are bigger than this, but it's above the atmosphere. It does not have to contend with atmospheric blurring. We calculated the diffraction limit of the Hale telescope. There's 0.025 arc seconds. That means Hubble, at half the size, its diffraction limit is 0.05 arc seconds, 1/20th of an arc second. And so it achieves that. Up there, it can image to a 20th of an arc second, at least for that wavelength of light. It can do even better if you go into the ultraviolet, where the wavelengths are shorter. But 20 times better than the atmosphere. That's not bad, that's great. And so if you need to make a really crisp picture, that's the way to go. and it's very in demand. People apply to use Hubble. It's a national resource. Not individuals, whole teams. A whole team gets together and they put together a proposal. And for every one that's accepted, there are about 30 that are rejected. It's that difficult to get time. I've been fortunate. I've been on, I think, 2 successful Hubble proposals, but just as one of many players to collect and make use of that data. Now, yeah, so Hubble is a lot better in that regard, but remember what we learned in lesson 3 in particular, that most of what we learn about the universe, we learn from spectroscopy, from taking the light and not making a pretty picture or a crisp picture, but not making a picture at all, just breaking it into its component colors and taking a spectrum. For that, you don't want Hubble, usually. You want the biggest telescope you can get, the biggest light bucket, collect as much light as you possibly can. So if I'm going to do spectroscopy, which is what most astronomers do most of the time, you pick the Keck telescope over Hubble every single time. But if you want that crisp image, go to space. Yep. Okay, so talked about 2 ways to battle the atmosphere, but I've saved the really good one for next time, and that is adaptive optics, where we actually monitor the atmosphere in real time, monitor how it's pushing the stars around, magnifying, demagnifying them, and then send commands to small mirrors built into telescopes that move and adapt to correct the atmosphere in real time, untwinkle the stars. Space age technology, and we'll present that next time. Okay, that's it for today. I'll stick around if you have any questions.
Thank you.
Thank you.
Thank you.
My pleasure.
Can you explain why the sunset and sunrise are red again?
Yeah, so you're scattering out, actually the dot cam's best. Or I had a figure here. I didn't use it, but it's the same idea. Suppose you're standing here and you're looking at the sun, and so you're looking straight up through the atmosphere. It means you're looking through not much atmosphere, just a little bit. It scatters some of the blue all over the place and makes our sky blue, but otherwise the sun's color is pretty much the same. But if you're standing here, the sun or the moon or planet, star, whatever you're looking at, but let's say the sun is on your horizon. It's a sunrise or a sunset. And so see how much more atmosphere that light has to pass through, because it's coming in tangentially, sideways. And so given that longer length of atmosphere, maybe 3, 4, 5, 6 times as much atmosphere, all the blue light gets scattered out. And a lot of the red light, but what's left behind is primarily red. And so you'll end up with a red sunset or sunrise. As we're looking at the star, at our sun, all the blue light's being scattered out of that line of sight.
Can you explain the second bullet point that just said "go up" with like
Go up, yeah.
arrow?
Maybe not the best choice of words, but lack of. Yeah, one way that you can beat the atmosphere is to go red, to longer wavelengths, and that's because, again, the atmosphere scatters red light less. So go red is one way, go to a longer wavelength. And then the other way is to go up, get above the atmosphere. Because if the atmosphere is the problem, just get above it. So tall mountains or space telescopes.
Oh yeah, thank you.
All right. Anything else?
Hi.
Hi.
I was emailing you about how I had like surgery and like the infection and stuff, and I wasn't able to take the exam.
Okay.
So when, what is the extension like? When do you want me to take it?
As soon as possible. When can you take it?
I could take it probably tomorrow
Okay.
or maybe Wednesday.
Yeah, send me an email with your preference, based on when you'll be well enough to do it. And did you send me the medical excuse yet? Like the
Mhm.
documentation? Okay. Just email me again on that email thread where the documentation is included, and just tell me when you want to take it. And I'll
Okay.
set the deadline to midnight of that day.
Okay, thank you.
Sure.
Thank you. Have a good one.
You too.